Okay, today is the third lecture on the introduction to the quantum feedback control. I have to unmute. Okay, perfect. Today I will introduce two parts. The first one is quantum stochastic calculus on the restricted exponential domain. And the second one is the quantum stochastic differential equation, which can help us to describe the interaction between the system and the field. Okay, firstly, let's start on the introduction on the quantum stochastic calculus. Now, here is a reference. In this first part, I will principally follow the treatment in this book.
Sorry, I still see, I'm not sure I'm seeing the same thing as you.
Okay, sorry.
Maybe I'm the only one, I don't know.
No, I agree. I also see the previous slides.
It's better now. Can you see the second one?
No, still on that same one there.
Still the same one.
Yes, same.
Okay. Wait a moment. New share, right? Yes. Share. Can you see now?
No.
Okay.
No.
Stop sharing. Okay. Where's the share screen? No, not that one. Can you see right now?
Yeah, things are moving now.
Moving. Okay, perfect. I just try to make presentation. Does it move?
Yes.
Move, right?
Yeah,
Yes.
It's okay now.
Okay, perfect.
Thanks.
Sorry. Okay, so here is and the first part is on the quantum stochastic calculus on the restricted exponential domain. And here is a reference. In this part, I will principally follow the treatment in this book, the first book, an introduction to quantum stochastic calculus. Okay. And firstly, let me just briefly recall what I taught in the last lecture. Some important notation and definition. The first one is quantum probability space. Okay, and a quantum probability space on a Hilbert space, it's a pair of fundamental algebra on this Hilbert space and a normal state on this fundamental algebra. And also there's a very important theorem, it's called Spectral Theory, which connect the commutative quantum probability space on the Hilbert space with the classical probability space, which means if a given commutative quantum probability space, and we can always construct a finite measure space and a star isomorphism, and also we can define a probability measure based on the normal state of the fundamental algebra. Okay. Which means it's a commutative probability space equivalent to the classical probability space. And the second one is a symmetric focus space. This space is also a Hilbert space denoted as the gamma S, and the H here is called single particle Hilbert space. And we also define several important vectors in this space. The first one is exponential vector in this symmetric focus space. And for each U in the parenthesis is a vector in the single particle Hilbert space. And also we define the vacuum vector. It's called E0. Okay, just the first element is 1 and the other is direct sum with 0. And the linear spine of the exponential vectors is called exponential domain, which is dense in this symmetric focus space. Okay. And next, we have also defined the three fundamental stochastic processes. And firstly, we define the well operator, which means for any vectors U and V in this single particle Hilbert space, and for any unitary operators U, capital U on this Hilbert space, there exists unique unitary operator, which is called well operator, and denoted by W, U and capital U on the focus space, on this focus space. And this action is like that. On the exponential vector, it's like that operation. And based on the well operator and Stone theorem, we can define two operators. The first one is called field operator, denoted by BU, okay, which is self-adjoint operator. And the second one is called differential, the second one, the lambda, denoted by lambda A, is called differential second quantization of A. And based on these two operators, the field operator and differential second quantization operator, we define the three fundamental stochastic processes on the focus space. The first two is called quadratures, denoted by QT and PT, which correspond to the Winian process under the vacuum state, okay. And for the based on the differential second quantization operator, we can define the gate process, which corresponds to the Poisson process in a coherent vector, coherent state. And then also an important result is for these three stochastic processes are commutative, but they do not commute with each other. Okay, let's start today's lecture. Firstly, I will introduce the quantum stochastic calculus, because the motivation is you want to describe the interaction between the system and the field, which need, just last course, we have already described the field. We can use some stochastic process to describe the field. But in order to describe the interaction between the system and field, and there's a choice, there's an option, is to use the quantum stochastic integral. But in the last course, we have already said some precise stochastic process, which is unbounded operator. So we have to face some domain problem, domain issues with respect to this unbounded operator. And the Wilson and Paradisi proposed an idea and method is to study this unbounded operator on a dense subset of focus space, which is called restricted exponential domain. And on this domain, we're allowed to calculate the strong limit, the limit in the strong topologies. Okay, and first, I give the definition of the quantum probability space on our whole space, which can include the system and the field. Okay, first is the Hilbert space for the initial system. In fact, initial system is our quantum system, okay, which interacts with the field, denoted by HS as a called system. And the phi s is the state, is a normal state on the bounded operator on this Hilbert space. And also the gamma is this Hilbert space, the focus space in the Hilbert space for the field. The phi f is a normal state on the bounded operator of this focus space. So we can define our quantum probability space, this tensor product of these two algebra, and the state is just tensor product of these two states on the system and on the field. Okay, and here, for the purpose of the simplicity and for easy to introduction, and in the following, we just consider the finite dimensional quantum system. So we suppose the Hilbert space of the initial system, the HS, is always finite dimensional. So for this part, we can avoid the domain problem. Okay, to study in order to introduce the stochastic integral, we have to use a very important property. It's called exponential property. And for the two Hilbert space, H1 and H2, there exists a unique unitary isomorphism which is denoted by U, between these two Hilbert space. Okay. We can write its action on the exponential vectors like that, which means we can transform the vector sum in the parenthesis to the tensor product of two exponential vectors. And this property is very useful. Of course, we can find I will not give the proof of this theorem, and we can find the proof in this book, in this page. Okay. And this property is very useful because it can help us to split the vector, the exponential vector, and also can split, decompose the focus space. For example, we adopted these notations, and we denoted Fs like that. Okay, which means they just function on the L2 and the L2 space of the positive half line, and we take the identity on this part, denoted by Fs, and which means we can decompose the function f in the three parts like that. And then by using the exponential properties, we can decompose our exponential vector like that. Of course, this equality is through this unitary isomorphism. And similar, we can also split our focus space, symmetric focus space, in the three parts. Okay, and of course, this equality is through the unique unitary isomorphism. And next, I will introduce another dense subset of the focus space, which is called restricted exponential domain. And denoted by D is the linear spine of the exponential vectors, and which F on the vector on the single particle Hilbert space it belongs to the L2 space and interaction between the L2 space and L infinity local infinity. And which is a subset of the exponential domain, and which is also dense in the focus space, in this focus space. And when we add this interaction, and heuristically, we can just think that this part can help us to prevent the Poisson process, the gauge process, from blowing up at a finite time. Okay. And for more detailed discussion on this part can be found in this article, on this introduction, article of the introduction. And next, we define the allowable operators. And then first, we define this space and the linear spine of the F tensor product with EU, with the exponential vectors. And F is a vector in the Hilbert space of the initial space. And the EU is belong to L2 and L local infinity. And if an operator X on this total space is called allowable, if its domain of this operator equals to this space, HS, and we call that the tensor product with the underline, we call that algebraic tensor product. The HS algebraic tensor product with D. And also, we suppose the adjoint on this space, the domain of adjoint on this space include the domain of this, the domain of X, of the operator. And then for any allowable operator X, we denoted the X dagger is a restriction of the adjoint of X to this space. And next, we give some definition on the process. Admissible process is a family of allowable operators. Okay, admissible process is called adapted if we can decompose our xt, our process, in such a way, which means which means in the xt just can acts on these vectors, which means we can decompose our hyperspace in the past space and the future space. Okay, which means if xt in the future space it acts just like the identities, and in the past space it lacks the x like some operators are denoted by the xt like that. Okay, which means this part works only on the past space, and for the future space is identity. Okay, and this is a very important definition, which is called adapted. Okay, next I introduce the three fundamental quantum noise. I just recall the three stochastic precise, Qt, PT, and gauge precise. And next we can introduce the annihilation precise AT. Okay, and here I just amplify our precise in the whole space, which means that the annihilation precise acts as the identities at the initial space, And similar for the creation precise denoted by the AT dagger. Okay, and we can given by this one, which means the annihilation precise and the creation precise is defined based on the Qt and PT. And we can also, it's obvious in fact, the creation, the adjoint on the HD, on H tensor product D is just the creation process. Okay, we have this relation. And also the gauge process, we identify the amplification on the whole space of the gauge process. Okay, here the three fundamental noise, quantum fundamental noise, and we'll introduce the quantum stochastic integral with respect to this noise, these three stochastic precise. And firstly, I'll introduce these properties. These properties on the field operator and differential second quantization operators. On the exponential vectors, which acts like that. And for the proof of these properties can be found in this book. Okay. And we will see this property is very useful to define the integral. Okay. Okay, the first is the lemma. We let MT be one of three fundamental noise: creation process, annihilation process, and gauge process. And for any S smaller than T is over positive, there exists an operator denoted by the lambda M between S and T on this space. Okay, this space is it's just the DST denoted by DST is a restricted domain space, and for the vectors, it's between sorry, I forgot this definition. Here's definition. For the F, it's between the L2 in the S and T and L infinity and S and T. And then I denoted by the DST. And we can there always exists an operator, sigma delta MST, such that we have this relation, which means MT minus MS on this vector, and the X like that, which means in the initial space and the past space, the X has identities, and just on this present space, okay, the present space, it acts like this lambda delta, sorry, lambda, this operators. And in the future space, it acts as identities also identities. This is very easy to show that, because we can just, because the three noises is adapted, which means we can decompose these three noise in the past space and in the future space. And also we have these properties, these properties like that. And we can easily obtain this relation. And now we just let this process LS be admissible and adapted, which means we can decompose like that. And this operator acts as identity in the future space. So we have this multiplication. It's just the tensor product of these three parts. Okay. Because the LS acts only on the past space and MS minus MT minus MS, just on the present space, and for the future space as identity. Okay, now we can define the quantum. We start to define the quantum stochastic integral, and we will follow the same procedure as the definition of the classical stochastic integral in the classical sense. I mean, something like the the stochastic integral with respect to the Brownian motion, for example. We'll start by the definition of the stochastic integral of the simple process. And next, we will find some estimation. And in the classical case, we have the Ito isometries. And this estimation can help us to extend to the simple process to the L2 process. Okay, we will do the same procedure here. And I will first give the definition of the simple quantum stochastic integral. An admissible process LT is simple, is just very similar to the classical case. If we can find a partition in the line, in the R, okay, in the R, and we have this expression, which is called simple. And now we let the simple process LT be adapted. And now the simple quantum stochastic integral on this space can be defined like that, just in the sum form. Okay. And here is called fundamental estimate, and it plays the same role as the Ito isometry in the classical integral. And here we have this estimation. For any simple adapted precise LT, we have this estimation. I will show in the following. This estimation is very useful to define the general quantum stochastic integral. And next here is a definition, the very important definition, which is called for the precise, which is called stochastically integrable. An adapted process xt is called stochastically integrable, and in the brief I just write an SI. If there exists a sequence of simple adapted process, so that it can approach to this space, to this adapted process, which in this sense, which means the limit n tends to infinity, and we have this integral equals to 0. Okay. And next we'll use a sequence of a simple quantum stochastic integral to approximate the quantum stochastic integral of the process, which is stochastically integrable. So this property of the process is very important, but how to verify this process, whether it's stochastically integrable or not? And here's the lemma, which provide the sufficient condition, can ensure the adapted process is stochastically integrable. If adapted process xt satisfy that, this mapping is left continuous and is bounded in this sense, then this adapted process is stochastically integrable. And for all the proof can be found in this book. Okay. Okay, next we'll start to introduce the quantum stochastic integral for the process which is stochastically integrable. And first, we suppose our process, the integrand, is stochastically integrable. And then we can find this, or we just use the fundamental estimation on this part. It's always smaller than this one, okay, by using the fundamental estimation. And obviously, it's a Cauchy sequence. So there exists a limit, and this sequence converge in the whole space, in the larger space. For all vectors, if tensor product with exponential vectors belonging to this space. And of course, the limit of this sequence does not depend on the choice of the sequence of simple process. And so we define the quantum stochastic integral for the process which is stochastic integrable, just by the limit of the one of the simple process, the simple quantum stochastic integral. Okay. And next, we define something larger. We give a definition of quantum stochastic integral. I denote by IT with respect to the four process: the gauge process, creation process, annihilation process, and tank process dt. I denote by IT, okay. And here is the two. Next, we will to derive the quantum Ito formula, which is quantum Ito formula, okay. And in order to derive this quantum Ito formula, we need two important lemma. And the first one is called first fundamental lemma, because they take this name in this book. And in the first fundamental lemma can provide the matrix element in this quantum stochastic integral. Okay. And we suppose this four process to be stochastic integrable. And then we can obtain this precise, we can obtain the elements of the matrix. We consider the matrix. We can obtain the elements in this IT, which is given by this one. This expression, and I just rewrite this expression in the matrix form. Okay, it's easier to read. And I'll give some outline of the proof. And this lemma, this first fundamental lemma, is for the four stochastic integrable precise. And we will firstly, of course, we firstly study the first fundamental lemma for the simple adapted precise. If it is simple, we can write something like in the sums form. Okay, it's very easy to show that. And we can find the proof of this part in this book. For the simple adapted precise is obvious, in fact. And next, we can obtain the first fundamental lemma for the simple precise. And next, we will make the sequence of simple precise approximate the stochastic integrable precise. And here I just give the example of the first part of the quantum stochastic integral. I just calculate the first part, and for the rest, the three part can be done in the similar argument. Okay. And next, we'll calculate this one. We just because our precise ET is stochastically integrable, which means we can write in the limit of a sequence of a simple process. Okay. And next, because the first fundamental lemma for the simple process, we can obtain this expression. We just make the two together. We can obtain this one equal to this one, and we make this one minus this one, and we can obtain this expression. Okay. And next, just we apply the Cauchy-Schwarz inequality with respect to this inner product. Cauchy in the HS tensor product, the focus space, we apply the Cauchy-Schwarz inequality, and we can obtain this inequality, and when I denote the CT and the supreme of these two functions. The U star with the conjugate of this function. Okay, U. And next, we just apply once again the Cauchy-Schwarz inequality on the L2 space, and we can obtain this expression. Okay, and because once again our ET, the precise ET, is stochastically integrable, which means this part converges to 0. So we have proved the first fundamental lemma for the first part, for the first integral, and for the rest of the three can be done in the similar argument. Okay, so we have now we can determine each element of the matrix IT. And for the second one, it's called second fundamental lemma. In fact, it can be done in the similar process, but a little bit complicated. But it's always just can be done by the straightforward calculation. The similar procedure, the first one we calculate, we can show the second fundamental lemma for the simple process. Next, we calculate the limit. We can approximate the simple one to the stochastically integrable one. For the second fundamental lemma, in fact, it gives the Ito's formula. It's very interesting for the second one because we know that IT and IT prime may be unbounded. So it's difficult to study the multiplication of these two unbound operator because it's not always well defined. We have to face the domain issues. And the method of Paradoxis and Houston is they studied the joint because the joint is always well defined on this space. So they can obtain just by, as I said, in the same procedures and the one in the first fundamental lemma, we can obtain this one. It's a little bit long, but in the following, I give a more easier way to remember this formula, this expression. Okay. And now we have already. Now what we want to do is we want to transform. We'll put the left-hand side part, IT prime, to the right-hand side part. And we need to do some. We need some lemma, some result, which can help us to do this transformation. If any stochastically integrable process their adjoint on this space is also stochastically integrable, and we can write the quantum stochastically integral in this way. Okay. So now we can derive the quantum Ito's formula. There's two quantum stochastic integral IT and IT prime. There's a first fundamental lemma. I gave the form in the matrix form. Okay, and then for the second one, in fact just with respect to the first part, we write in his adjoint. So we can put this adjoint to the right-hand side, and we can obtain the multiplication. And just do the comparison between the first lemma in the first fundamental lemma and the second one, we can determine each element of this matrix, of the matrix of this multiplication. Okay, which means this part corresponds to the ET here corresponds to the d lambda t. And we can just do the comparison in the same way. Okay. So now we have the quantum ethos formula. And we write the quantum stochastic integral in this differential form. And we suppose every multiplication is well defined and every process is stochastically integrable. And then we can obtain the form of multiplications. I mean the differential of IT prime times IT is given by these three terms. Okay. And for the terms times with d lambda t, we can see that the IT prime ET, ET prime IT, and the ET prime ET is exactly this part, okay? This part, which can be determined by the first fundamental lemma, ET, corresponds to the d lambda t. And then we do the similar things for the rest of the three parts, and we can obtain this formula, which is called quantum ethos formula. And here is the table. It's very easy to remember these rules. So perfect, we have already the stochastic calculus into rules. And next, we can start to describe the interaction. We have already the tools. Next, we'll start to describe the interaction between the system and the field, which can be described by the quantum stochastic differential equation. I will also follow the treatment in the first book. Here's some motivation, the principal idea. What we discussed, what I talked on the first part, we have already defined the quantum stochastic integral on this space, but it is symmetric. It's just a symmetry on this space, and this space is dense in the whole space. That's a problem, because for the symmetric operators may have many, even no self-adjoint extensions. If we have many extension, the self-adjoint extension is a problem because we cannot interpret this quantum stochastic integral as an observable. We cannot analyze this observable, these operators in the quantum probabilistic framework. And then the Hewson and the Paradasi found some necessary and sufficient conditions which can ensure such quantum stochastic integral to be bounded on this space. It's very interesting because if this operator is bounded on some dense space, we can extend to a unique bounded operator on the whole space. And of course, just remember again, we always suppose our initial space is finite dimensional. Okay, and first, introduce for the general quantum stochastic general quantum stochastic differential equations. And the further theorem gave the result on extension and uniqueness of the solution of this equation. Just we suppose HS to be finite dimensional, and the four time-dependent process, is bounded, or suppose it's bounded process of the form like that, which means they act as identities on the focus space. They just abandon precise on this finite dimensional space. Okay. And then there exists a unique admissible adapted process, VT, as the solution of this quantum stochastic differential equation. And here we adopt these conventions, which means the VS, we can commute the VS with these four notation as we wished. Okay. Because in some book, we can find the VS just right here, not the outside of the parenthesis. And the proof of the theorem is very easy, just a straightforward of the Picard iteration argument. It's very easy, and we can also find the proof in this book. And here we just consider a very simple case. Is our HS, initial space, is finite dimensional. And for the focus space, the multiplicity of the focus space is just one, which means we have only a finite dimensional quantum system interacts with a single field, electromagnetic field. But of course, there exists the result on a general case. We can find the discussion of the unbounded coefficient on the infinite dimensional case, an infinite dimensional initial space with the infinity multiplicity in these two books. Okay, this is a book and this is a lecture note. It's also very well introduced in this part. Yeah. Yes. Very clear, in fact. Okay. Okay, next. Introduce the condition which can ensure the previous quantum stochastic differential equation to be bounded. In fact, it's not just a bounded, it's unitary. And we can just find, for example, we suppose that L1, the 4, and here I just write the form in the differential, in the quantum stochastic integral in the differential form again. Okay. In fact, the two are the same. And we suppose that the initial value is identity. And the solution is unitary if and only if the 4 precise is in this form. Okay, the L1, L2, L3, L4 in this form. Where of course the 3 precise WT, LT, and HT are bounded precise, and they just act on the initial space. And where the WT is unitary and HT is self-adjoint. So we just denote, we call this equation in this form by the HP equation. Okay, we realize that. And I just remark again, this equation is a very simple case, okay, very simple case, because our focus space, the multiplicity of our focus space is only 1. And of course, we can generalize to the infinite case. But there is also some things very important I want to emphasize here. The solution of the UT here is unitary adapted precise on this space, but it's not a group. It's not a group. It doesn't satisfy the group properties. It's a problem. But luckily, we can transfer this unitary adapted precise to a strongly continuous group of unitary operators by this one, where the theta t is the second quantization of the left shift operator. Okay, the theta t, the action is given by this one. The smaller theta t is just the left shift operators, and the capital theta t is a second quantization of the left shift operators. And now for the VT, it's very nice, a strongly continuous group. But in fact, in the following, we can see that in the real calculation and analysis, the UT is sufficient. And for the definition and the introduction of these operators can be found in this paper, the second one. Okay. Moreover, in this paper, they have also defined the Hamiltonian with respect to this to the solution of this equation. Okay. And next, we define the quantum stochastic flow, which can help us to describe the time evolution of bounded operators on our initial space. And in fact, our initial space is finite dimensional, so it's always bounded. It's not a problem. We suppose we have this HP equations, given this one. For example, just some motivations. And let's suppose the WT is identity and LT is 0. Okay, then this equation, HP equations, transform to a classical Schrodinger equation. And where HT is Hamiltonian HT. Okay. And this is why in this article, in the article of the famous article of Husserl and Paratasi, they called their HP equation as the noisy Schrodinger equations. And given the observable X on initial space, and we can define the quantum stochastic flows and the JTX. Okay, and in this form. As I said, in fact, the UT is not the growth, but just in this paper, sorry, it's 2. Okay, it's 2. In this paper, we can define the strongly continuous group of unitary operators, and this one, something like that. Okay, so we have the Heisenberg picture. In the Heisenberg picture of this observable, which describes the time evolution of this observable, can write in this form. And obviously, this operator, the second condensation of the shift operator, commute with this one, because in this part it's identity. Okay, so it's commute with each other, and then we can write in this form. So in fact, this form can describe the time evolution of the observable. And next is some results, some properties on this flow. Just by applying the quantum Ito's formula, we calculate the derivative. Just by applying the quantum Ito's formula, it needs some calculation, but it's not difficult. It's just straightforward, but it's a little bit complicated. It's long calculation. And we can obtain this form. Okay, we can obtain this form where the LT star is very interesting, this part, because LT star is a joint of Lindblad operator. A joint of Lindblad operator, and it's given by this expression. And we suppose the initial value is just observable, okay, of the X transport identity on the focus space. And we have the X, this map, the star homomorphism from the abundant operator on the space, on the initial space, to this part. Which means just in the future space, it acts as identities, and in the initial space and the present space is some bounded operators. Okay, and of course, for any observable on the initial space, this map is strongly continuous. Okay, this is obvious because our UT is strongly continuous. So now we have UT. Sorry, I just remember again, our UT here is unitary operator. If it's unitary, it's bounded, of course. We can extend to the whole space without any problem. And next, it's similar. In fact, this part is very similar. It's very close to the first lecture, when I introduced by some physical argument. We can reobtain the master equation from the quantum stochastic flow. And in the first course, I called this equation as the quantum logical equation. Okay, but we can consider this equation, this quantum stochastic flow, as the quantum logical equations in the quantum probability framework. Okay. And of course, we need, if we want to start in the probability framework, we need some quantum probability space. Okay, it's a very large space, it's large enough. And where the Hilbert's, because for the initial space is always finite dimensional. So the NS data in the finite dimensional space can always be described by a density operator, density matrix on this initial space. And for the field space, for the focus space, we use the vacuum state. Okay. And then we define a TT, a map TT, by averaging the quantum stochastic flow under the vacuum state. Here is the expression. And then we can obtain, and once again, we can apply we have already the expression of this one by applying the quantum intuitive formula. And we can obtain the expression of the TT, which is given by this one. The L star is a giant Lindblad operator. And this map, in fact, is a one-parameter semigroup of completely positive linear operator in this algebra. It's in the bounded operator, in this algebra, BHS. Okay. And just by this relation, in fact, we can reconstruct the master equation, which describes the time evolution on our initial space, which describes the time evolution of our density operator of our space, the quantum system, main quantum system. And here the PT is a one-parameter semigroup generated by Lindblad operator, L. Okay, which means our quantum stochastic flow can provide more information than the master equation. Okay, very interesting. And next, we will try to, because what we discussed is always on the mathematically. There's no emergence of the physics, and now we try to immerse some physics application in these HP equations. Okay, let's just consider the finite dimensional main system, the quantum system interacts with an electromagnetic field. And the dynamic of the whole system can be described by this equation. Okay, we can find all this discussion, the proof in these articles. And by the weak coupling limit, this function converges to this one. And in fact, it's obvious this equation is exactly our HP equation. So there's some sense to study that for the physics for the physics domain. Okay, and we discussed about the evolution of our system can be described by this part, by the quantum stochastic flow. Okay, and here we just consider our system is measured by the homodynamic detection and under the vacuum state. So we'll just get rid of the gauge process. We don't see the gauge process again. Here is only the differential of the annihilation process and creation process and DT, of course. Very interesting. We have already evolution of the system, but we also want to obtain the influence of the system on the field. Okay, which means we want to observe the field after the interaction with the quantum system. And maybe something just heuristically, we can write like that. Okay, we suppose Vt is our input field. And we will here for the homodynamic detection, for the special case of homodynamic detection, we suppose Vt is At is the creation process plus the annihilation process. And we know that these two processes is on the space HS algebraic tensor product with the D with the exponential domain. And this operator is essentially self-adjoint. So perfect. This one is correspond to the Qt, okay, what we defined before. And the YT is correspond to the output, which means after the interaction with the input field and the system, which is called observation precise. And then we can obtain this pair, this we call the system observation pair, by the homodynamic detection. The first one is just the quantum stochastic in the flows, and the second one we calculate derivative for the observation precise. Okay, just by applying the quantum ethos formula again. And here, of course, the L star is a joint of Lin-Bland operator. And here we suppose the X and L are constant matrix on this finite dimensional space in this form, okay, which means they always, the X only on the initial space. And HT we suppose is time dependent. And H0 is called the free, sometimes it's called the free Hamiltonian. It's a Hamiltonian of the system itself. And this part, HJ, is called control Hamiltonians. And we know that if we want to control the system, we need to add something external power to control the system. They need to be open. Okay, but if we suppose this interaction is very weak in some sense, we can write the Hamiltonian in this expression, okay? And where the bounded scalar function, real function ut, related to the amplitude of interaction between system and the control field. Okay, I just give we see this picture again. And this magnetic coil is our control field, okay? It's our control field. And the amplitude of this magnetic is denoted by, here it's called BT, but I denoted by the UT here, okay? Which means the system, the finite dimensional system is spin. And it interacts in this cavity with the field, input field and output field. And we observe the output field by the homodynamic detectors. And then we control this system, we control our spin system by these magnetic coils. Okay. And here the UT, the T, is just the function of a time. There is no feedback information involved in this function. So we call this type of control is called open loop control. There's no feedback. Very nice. We have obtained this system observation pair under the homodynamic detection. And we have already seen that in the first lecture by some physical argument. But in fact, we have still the problem of observation. Because I just introduced this part very quickly, there's two problems. Does this observation process make any sense? We know that this UT is not a group. The UT is a solution of the HP equation. It's not a group. But due to the result, we can construct a group, a strongly continuous group, correlated to the UT, denoted by VT. Does that make any sense if you write like that? And I called this precise YT like observation precise. Can we observe this precise in the laboratory? And for this part, I will introduce in the next lecture. And next lecture, there are two things very important on this observation. The first one is this precise, in fact, is already in the interaction pictures. So this one is makes sense. Okay, for the second problem can be also by the property of observation process, which is called self-non-demolition process, self-non-demolition properties. And for these two, I will introduce in the next lecture. Thank you. Okay. Let's stop the share.
Okay, any questions?
Yeah.
Let's see whether other people have any questions. Unfortunately, the two experts, Ticozzi and Tristan, could not attend today. They had some other obligations, but let's see whether other people have a question. I mean, I have a, I mean, maybe we are going to see it, or maybe we will not, but you see, you're introducing this machinery to describe a very particular physical process, which if we are going to work in, let's say, non-relativistic approximation, we can just actually write a Hamiltonian.
Yeah, yeah, exactly. Wait a moment.
I mean, the real Hamiltonian of the couplet is, right?
Yeah. Wait a moment, I just show you where is it? Here, this one, in fact.
No, very good. Okay, so there's a paper about that, which is, and then I guess I mean, it's kind of obvious, but just to clarify that there is a process of there are systematic approximations that you're using in order to arrive at this equivalent descriptions that is given in the terms of quantum stochastic calculus. Of approximation that you call decoupling limit, I guess. Maybe there's not a great terminology, but in the end you arrive at now you do the same thing in classical physics. You don't